because of spring break, is lab. Unless you want to do the lab over spring break.
No,
I'm actually so good.
I don't need it.
Just to clarify then, our lab that we completed a week and a half ago, roughly,
Resistivity.
is not due until next Wednesday.
Correct. If you've done it already, handed it in.
Wait,
great.
so resistivity is next week?
Resistivity is due next week, because it's due the next time that we had the lab, but we had a test last week,
thank
spring
God.
break this week.
That's what I'm saying.
I worked hard on that this morning and I was like, okay.
I walked into class last Wednesday and was like, I don't have the lab done, and then I was like thinking I had to give it in, like turn it in, but I only,
Okay, that's fine with me.
Now, if you've done it already, you can just sit back and there are at least 2 people who haven't finished, so you can just sort of laugh to yourself or laugh at them, whatever.
Okay.
And for those who have finished it already, then the people who aren't done yet said, I can't believe you stressed out over that, you got time.
I worked hard on that today, so.
Part of your-
Didn't finish it completely because I had a couple questions, so.
This is a lot of analysis questions.
There's so many.
Especially on, I think it was
But going through them one and
C, analysis C got me. I'm still confused on a couple questions on analysis C.
There's one question on analysis, A or B that I have. I was like, okay. No idea.
So are we introducing a new chapter,
Yes,
Right now.
23?
yes, right now.
Let's do it.
Enters one of the giants, Faraday. One of the few units that we have that's not actually the name of a person. The unit named after him was the Farad. I don't know why they didn't bother calling him the Faraday, but I was not consulted. All right, so Faraday was doing some experimenting. So he had the crude battery, so got a plus and a minus side there, and he had this wire. And so, we'll throw a switch in there. So there's a switch, so he can basically connect this or disconnect it however he wants. He had another loop of wire nearby, connected to a galvanometer, which is just from context, it's just basically a sensitive ammeter. In other words, it's going to measure current. And it's usually presented as sort of, figured it out accidentally. But he would make the connection here, and suddenly the ammeter dial would twitch, and then go back to 0. Then he would disconnect it, and the needle would flip the other direction, and then back to 0. Completely different circuit. But he was noticing that basically creating a connection here or disconnecting had an effect on the separate wire. You'll play around with it a little bit, and so you can try the same thing, except you've got your ammeter here, and then you got a really skinny wire, or really skinny wire going that way. The needle did not flick as much as it did if it was closer to a circle. And so then he began to try to figure out what the deal was. And he realized that, yes, I'm creating a current, but if I'm creating a current, what else am I creating?
The magnetic field.
Absolutely. And what he figured out is that the change in the magnetic field, so it's not the magnetic field itself, it's the change in the magnetic field, causes a secondary current. Now, he presented, the story is that he was presenting this to a group of reporters, and one of the reporters said, yeah, what use is this? And his response, although I have heard it attributed to others, was of what use is a newborn child. This is the basis of all power generation, I shouldn't say all, of power generation through most of the world. That's where this ends up being.
I guess I'm sad.
That's so funny.
Savage, I think the kids are thinking.
Yeah, savage.
As the kids are saying sad.
Yeah.
He was not saying they were useless, he said that they grow up to be somebody.
Yeah.
Now, Faraday has the law named after him, it's called Faraday's law. However, Faraday comes out with this in, I think, 1820s, somewhere in that, give or take 15 years. Meanwhile, there's another physicist, or what we would now call a physicist, also working on it by the name of Lenz, who actually develops the math behind it. And so even though it's called Faraday's law, Lenz gets credit for the minus sign. So what he figured out was that the change in the magnetic flux for time is equal to I'm suddenly blinking. Oh, okay. Is basically equal to voltage. Is a symbol for an EMF. And then there's this minus sign in front.
Is that an epsilon?
Pardon?
Is that an epsilon?
Yes, it is. So the change in the magnetic flux causes there to be a voltage, causes there to be a potential difference, which causes current to flow. This is what was figured out. So this is called Faraday's law. Lenz gets credit for the minus sign in front, but it really is Faraday-Lenz's law. I think Faraday came out with the concept first, Lenz came out with the math to formalize it. And so I believe they both should share credit. But in the textbooks, it's generally called just Faraday's law. All right, so a couple things here to unpack. One, EMF is just sort of an ideal voltage. Magnetic flux. We've talked about it before, but what is magnetic flux?
Electric flux is like the amount of electrons passing by a certain area in a certain amount of time, right? So
That's
it's
current.
Okay. Yeah.
But what is electric flux if you don't remember magnetic flux?
Isn't it flowing out?
I thought it was, I don't know. I thought it was what I just said, but if it's not that, I'm not sure what it is.
Does flux doesn't have anything to do with time?
Flux in and of itself does not have anything to do with time.
It had to do with that piece of paper and like how much of it was hitting the paper.
Like electron density. I don't know.
Not electron density.
Charge density?
There was a sigma in there, I think.
Was it the density of what it's passing through? Isn't that relevant?
Density of what? Although, density is the right word? There.
Right, area.
Or thickness, or I don't, it just seemed like, I remember when you,
We're talking about arrows being shot across the room.
yeah, so when you changed the position of the paper, it impacted how many were hitting it or not.
Yep.
So area, surface area should be in the formula.
Okay.
Or some kind of area.
E times
Wasn't-
A.
The surface area, like the paper.
Yeah,
What is
like
E?
E dot A, and then like charge enclosed.
Yeah, that's related but separate at the moment. E dot A, what is E?
The electric field?
Yes. So electric field times the area, dot product. Here, magnetic field times the area. So if I have a long wire here with a current moving to the right, it creates a magnetic field. So if I have a separate loop of wire, this current is going which way through this? Try that one again. If the current's coming this way, that creates a magnetic field going, and the magnetic field is going which way through this?
Out of the door?
Yeah,
Yeah.
coming out. So whatever that magnetic field is, now it does vary, it's gonna be stronger here than it is here. In a calculus-based course, that's legitimate to not give you much more information. What I would do for 152 is just to say, assume that the value at such and such a place is considered the average. So we have a magnetic field coming through this, and we have a certain area here, and so my magnetic flux would be based upon the magnetic field times this area. Average magnetic field times the area. Is a voltage created? So I got this steady current flowing off to the right. Is a voltage created here?
I guess we have to involve time to know that since time is in the formula. No?
Time is in the formula. So is the magnetic field changing with time?
No.
Why not?
Because the current isn't changing?
Yeah.
Right.
So-
Yeah, I commented, we have a steady current flowing. So if current is steady, the magnetic field is steady, there's no magnetic flux. Suddenly, whatever's creating this current here stops. So battery dies, whatever it happens to be, and so my magnetic field suddenly drops off to zero. Now I have a change in the magnetic flux because there's a change in the magnetic field. Now I'm going to create a current in this loop here. The question is, which way is the current going to flow? And this is the importance of the negative sign. In and of itself, it's very difficult to look at this and go, oh yeah, the negative sign clearly tells us that the current's going to flow in such and such a direction. But we can think through it. All right, so we have the magnetic field collapsing here. The question is, does nature want to make it collapse faster or make it collapse slower?
Slower would be my guess.
All right, let's think about that as true. Let's reverse it. Suppose we suddenly get a new power supply here and the current starts cranking up. And so now I have a magnetic field that's being created here. Because remember, this current that is flowing through here will create its own magnetic field. If that magnetic field that the current creates is in the same direction, what's going to happen?
It's in the same direction as what?
As the magnetic field. So this magnetic field that's changing causes a voltage in the loop here. The voltage in the loop is going to cause current to flow. As that current flows, it's going to create a secondary magnetic field. If the magnetic field is in the same direction as this magnetic field, what is going to happen?
Maybe a stronger magnetic field?
So it'll become stronger, which means there's a change, which is going to do what?
Change our magnetic flux.
Which is going to do what to the current?
Change the current.
Pardon?
Change the current.
How?
Gonna increase,
It's gonna,
So my current has increased, so what's that going to do to the magnetic field?
increase it again.
Which is going to increase the current again, which is going to,
So it goes back and forth.
sorry, what was that, Brooke?
I was just like it feeds off of each other.
Yeah, which would be bad. If it if it made it increase faster, then basically you're going to get a runaway and you'd have a magnetic field that just get bigger and bigger and bigger, and eventually something's going to fry.
basically it's like positive feedback.
Yes, and nature doesn't like that. The minus sign there is telling us it's going to try to do the opposite of what's happening to the flux. So when it starts to collapsing, the current in here is going to create a secondary magnetic field that's going to try to slow down the collapse. When it's building up, so when I first create the current and the primary current, the secondary current is going to try to slow down the increase of the magnetic field. or magnetic flux, I should say. So, in terms of practical aspects, if, call that I1, if I1 collapses, probably goes to 0, then the magnetic field in here changes. I guess the field collapses. The secondary current will try to slow, or will slow, the change in the magnetic flux. So if my magnetic flux is going to 0 here, well, there's only really two things that can be done to change the magnetic flux. Either I change the magnetic field or I change the area. It's not going to change the area in this particular problem. So what's going to happen is it's going to try to make the magnetic field stronger. Because my magnetic field is collapsing, my magnetic flux is getting smaller, and so the secondary current is going to create a secondary magnetic field going counterclockwise. When we start it up, so I goes from 0 to something not 0. I have a magnetic field that's suddenly getting bigger here. It wants to slow that change down, and so what it's going to do is create a current flowing this way. This will create, the secondary current here will create a magnetic field going into the board, which is going to slow down the increase in the magnetic field that's coming out.
Dr. Fox?
Yes.
I'd sort of like to understand how to determine the direction of the secondary current and magnetic fields from the first set. Like, I don't understand. I understand if the current is flowing this way, that the magnetic field inside this area would be coming out of the board. So if we have a magnetic field coming out of the board, how do we determine the direction of the secondary current and magnetic field?
My flux is increasing when I turn this on. When I flip on the battery, my magnetic field is increasing coming out of this because of this one. Because I don't want it to increase too quickly. This induced current is going to go around the wire in such a way as to make a magnetic field going in the opposite direction.
Okay, so this is why you're saying nature doesn't like that.
Right.
That was your reasoning for why it goes in that direction.
Correct.
Okay, I got it.
Yes, we don't want a runaway process.
Right. Okay.
And apparently neither does nature. I suspect that if the negative sign should not be there and that the increase would happen, I think we as a species probably evolved differently or annihilated ourselves long ago. Because if you think about it, if a change in the magnetic field made the magnetic field stronger, I could take a copper pipe, put a magnet on this end and just give it a tap, and the thing would just start moving faster and faster, leading to weapons.
Lead to weapons, yes.
Always
That's my
listen to
favorite
what's
quote.
Other questions at the moment? So let's do another induced current, creating a magnetic field, and then we'll start talking about changes in area. So I have an isolated magnetic field here, of course coming out of the board for usual reasons. I'm gonna call it B sub 1, just because it's the primary. I don't know what's creating this magnetic field. This magnetic field exists and I've got it trapped in this small area here. I have a loop of wire that I'm going to move to the right. So as this loop of wire is moving, as it moves here, So as the front edge gets to here, what is the current flowing through this? So we're talking about when it gets to, it's at that point, still moving to the right. All right, I will say right now that you're overthinking it.
Can you explain what we have going on here again?
All right, so I've got a magnetic field within this area right here. So there's no magnetic field anywhere else, just within this big rectangle.
Okay.
I have a loop of wire or square of wire. It's connected, even though that connection disappears. There we go. I now have a complete loop here, just sitting there, and that loop is moving. When the loop moves from here to here, the question is, what is the current that is going to be induced in my wire?
Is it going to be
Is
the
it-
same,
yeah.
no matter the distance from the magnetic field,
What's going to be the same?
the current?
And what would that same be?
Is it to the right?
Is there like an actual value or?
Yes, there's an actual value.
I don't know.
When you said to the right, what did you mean?
I thought you were talking about the direction. I thought you were talking about like the direction it was like impacted by the current or by the magnetic field. Sorry, but it's not in the magnetic field. It's outside of it. So okay.
That was a key thing you just said.
Okay.
Oh.
Yes?
Is it zero?
Why?
Because it's not being influenced by it, it's outside the magnetic field?
It is outside the magnetic field. There's no change in the magnetic flux, so there's no induced current.
I let Zach. I threw an alley-oop to him and just let him kind of finish.
Excellent.
You just dumped it.
Yeah.
Like Derek Wittenberg to Lorenzo Charles. And I assume none of you know the reference,
No.
unless you're a huge NC State basketball fan.
That was that was
Not NC State.
that was my dad was a freshman in college when that happened.
As
With
was I.
Jimmy V.
Pardon?
Jimmy V.
Yeah.
Oh, yeah.
Came